Good morning. Happy Wednesday. Glad to see 60% of the class here after the exam. The average was 75.8, median was 79. So good job. We'll be handing back the exams in the SME atrium after class. So if you want your exam, that's the best time to get it from Cody and Mickey. Today we will be starting a discussion of digital technology. Why is that relevant to nanoengineering? Well, digital technology, computation, memory, storage is perhaps and information technology. I shouldn't really have to say this, but it has transformed the world, right? And it's really a manifestation of nanoengineering principles. So you can't make a microprocessor without being able to make, you can't make today's microprocessor without being able to make structures on the order of 10 to 20 nanometers. So really small stuff. Digital microprocessors have really been nanoprocessors for a long time, but the joke kind of is that what makes nanotechnology special, that is the effects of size confinement, are something to be suppressed in microfabrication as opposed to something to be exploited, because you don't want you don't want charge carriers tunneling necessarily between through your gate dielectric and so on. You don't want your capacitors to leak, which they do if you're not careful. So sometimes we want to suppress these quantum phenomena, but really many of you will end up working in the nanofabrication field. So my PhD is actually in nanofabrication engineering, and it has applications in biotechnology. So the company Illumina, which most of you have heard of, which is the leading genetic sequencing company. So something like 90% of all genetic information ever measured in humans was done on Illumina machines. And at the backbone of that technology is chemical patterning of surfaces and topographic patterning of surfaces to do sequencing with large throughput, that is done using techniques that were developed originally for the microelectronics industry. So in order to sort of prime the pump for a discussion of micro and nano electronics, I want to talk a little bit about digital computation in general. Now, we're not going to go into very much depth, but it's worth knowing the first few things about binary and digital. Digital and binary are not the same thing. You could have all binary computation with digital computation, but not all digital computation is binary computation. You could have digits that use a different number system, so not just binary, but ternary, but it's significantly more complex. You wouldn't use decimal, which is what we think in, just because if you're going to measure 10 different gradations per signal, you might as well just make it an analog system. And there are advantages to using digital as opposed to analog, because it is more difficult to introduce errors in a digital signal, and also it's easier to encode information in the forms of ones and zeros, which are encoded as ons and offs of transistors, or charged or uncharged capacitors. And to separate a zero from a one, you just have to establish some thresholding value. Anything above that is a one, and below that is a zero. In the case of digital information storage, for example, in optical or magnetic media, you only need something to be able to switch states, right? So in the case of a CD, which is an ancient technology that stood for compact disc, there was a data track Now in 1982, compact discs, or CDs, certificates of deposit, compact discs were like 780 megabytes. And in 1982, the average hard drive size was like 3 orders of magnitude lower than that. And most computers actually didn't have hard drives. They were like floppy disks, and which also encoded information magnetically, but they didn't use, but the magnetic domains were much larger scale, so you couldn't fit as much information on a floppy disk as you could on a CD. On a CD, the structures themselves, the bits on a CD, are like 800 nanometers square and 100 nanometers deep. So we're already almost in nano technology in 1982. And when you and if you peel a CD apart and you look at it under a microscope, you find that the data track are pits and lands. That is LANDS, so pit, land, that that encode the information as either a 1 or a 0. In that case, we have these 2 layers of relief. The structure is made by by injection molding of a polycarbonate thermoset into a mold that was mastered by something called electron beam lithography, where you use an electron beam to render soluble an electron beam resist in the pattern of the music rendered digitally, and then you wash away the exposed regions, you metallize it, then you pour the polycarbonate on, and you press it and you cool it, and then you get the data track. Then you sputter coat it with aluminum to make it reflective, which is what we normally see, which is why they explode when you put them in the microwave. And then you coat it with an acrylic plastic, and then your label, which is like Britney Spears' Greatest Hits Volume 2 or something. So digital technology, this is really the most famous or well-developed branch of nanoengineering. So basically all of your tablets and phones and computers are really based on nanofabrication engineering that's been developed. The computer scientists like to claim it for themselves, but without chemically amplified photoresist and e-beam lithography and photolithography and really nanofabrication engineering, none of it would be possible. So you can't program a chip that you can't fabricate, right? So we have digital as opposed to analog systems. And you'll notice that as the memory capacity and computational power of digital systems has increased, it has replaced analog forms of information storage and processing a little bit at a time. So even when you're growing up, when you're a little kid, most of your TV channels were analog signals, and they were all more or less changed to digital. And in fact, the old analog frequencies by the FCC have been cleared away mostly for other uses. You notice that at the movie theater, we're increasingly going from film projectors to digital projectors. Even the way that movies are filmed is going from analog film to digital recording media. And really, we weren't able to do this until fairly recently, because you just couldn't encode enough information and store all the information digitally to do it. But in cases where it's desirable to do it, we definitely want to if we can. So analog, some adjectives that describe these are continuous, continuous signals. Digital signals are discrete. Analog technology is the quantities are measured. And in digital technology, the quantities are counted. So in cooking, you measure things like flour or sugar, cornstarch, whatever, and you count things like eggs. If you know that something is only one discrete unit, like an egg, it's impossible to make an error, right? It's like, oh damn, I accidentally added an extra third of an egg. Unless you spill it, I guess, which is possible. But it's not possible in our argument. Analog signals. It has, I was going to ask if anyone's ever made a mixtape. Yeah, right. So, when I was a boy, I would make mixtapes before CD burning was a thing. And I'm not that old, but I still did make mixtapes. When you make a mixtape, and you make a mixtape of a mixtape, and a mixtape of that, and a mixtape of that, eventually the sound quality becomes very, very, very crappy. But no matter how many times you burn a CD or copy an MP3 from iTunes to a million different devices, the quality never degrades. It degrades when you compress the signal originally, but once you have a digital object, the quality never degrades. So analog technology has error prone reproduction. And digital has facile, meaning easy reproduction. And analog in general, let's say imprecise. Digital, precise. Digital computation is done in binary. So ones and zeros. Normal counting is done in decimal. We don't think, oh, I count in decimal. Yeah, well, everybody does. Let's break down a decimal number and see if we can see what we're actually doing in our head as we look at a number like 3,871. When we look at a number 3,871, what we're doing implicitly by ordering the numbers in this sequence is we give each one a weighted position. The weighted position starts with 0, 1, 2, 3. And what we are implicitly doing is we're saying this is a coefficient times the number system, which is 10 for decimal, raised to the power of the weighted position, plus 8. So 3 times 10 to the 3, plus 8 times 10 to the 2, plus 7 times 10 to the 1, plus 1 times 10 to the 0. Or this is the coefficient, and this is the system. So decimal. Great. I just taught university students how to count. Binary, you can see where I'm going with this. Binary is exactly analogous, except decimal is in a sense harder because there's a more effective complexity, because we have to memorize 10 symbols in order to know what this means. So there's a lot of effective complexity embedded in here, namely that we had to know what all 10 symbols were. But computers are stupid, and they only know 2 symbols. And our future AI overlords are going to strike me down for saying that computers are stupid. But anyway, they work best in units of where they only have to memorize two symbols, because high voltage in a transistor, high current in a transistor, high voltage in a capacitor, a magnetic domain in a hard drive pointing up or down, a capacitor in a memory device being charged or uncharged, an optical storage medium being either a pit or a land, nothing in between. It's much easier to store and process information in this way. So in this case we have 8 weighted positions, and we have 0, 1, 2, 3, 4, 5, 6, 7. So we calculate this number, convert this number from binary, which some alien species can probably look at that and tell you exactly what it is. Maybe some people in this room can. I definitely can't. In order to tell us what this number is, we need to do our same. Somebody get it in their head? We have 1 times 2 to the 7 plus 1 times 2 to the 6th plus 0 times 2 to the 5th plus 0 times 2 to the 4th plus 1 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 0 times 2 to the 0, which is 128 plus 64 plus 0 plus 0 plus 8 plus 0 plus 2 plus 0, or in decimal, 202. Easy for us because we're good at effective complexity. We're good at memorizing all the meanings of all 10 symbols here. This is easy for a computer. Converting the other way is a bit more tricky. If you had to start with a decimal number and convert it to binary, you kind of have to use a mnemonic device, which is the division by 2 method. So decimal to binary, repeated division by 2. So let's make a table, division, quotient, remainder, and then the binary number. So we'll go back. We'll see if 202 can be converted to 11001010. So 202 divided by 2 gives you a quotient of 101, a remainder of 0. And you put the remainder on the right-hand side of the binary number. Then you have 101 divided by 2 gives you a quotient of 50, a remainder of 1, and the binary number of 10. Remainder goes here. 50 divided by 2, 25, 0, 0, 1, 0. 25 divided by 2, 12, remainder of 1, 1, 0, 1, 0. 12 divided by 2 is 6, remainder is 0. 0, 1, 0, 1, 0. 6 divided by 2, 3, remainder 0, 0, 0, 1, 0, 1, 0. This is fun, right? Almost there. 3 divided by 2, 1, remainder 1, 1, 0, 0, 1, 0, 1, 0. 1 divided by 2. I had to look this up. That's 0, remainder 1. It's 1, 1, 0, 0, 1, 0, 1, 0. Because I hadn't worked with remainders in a while. Okay, so like magic, we reproduce the 1, 1, 0, 0, 1, 0, 1, 0. Okay, let's look at the way that we write these binary numbers. In decimal, we separate units by a comma, at least in the American English system. Sometimes scientifically or in British journals or something, publications, you'll see a space here instead of a comma. In binary, we separate it by a space. We separate groups of 4 by a space. Instead of groups of 3 by a comma, it's groups of 4 by a space. Each unit, so binary numbers have the number of binary digits have cute names. So 1 is a bit, 4 is a nibble, 8 is a byte, 16 word, 32 is a double rainbow. Just kidding, word. Usually in computers, information is processed in units of bytes, which is why we only ever see bytes. Well, no, sometimes we see bits. Usually we see bytes, megabytes, gigabytes, terabytes. In fact, I'm told by people who do this for a living, that even if you are to encode something that requires less information than a byte, like true, false, and of course you guys know this because you guys are computer savvy, you don't encode it as 1 or 0, you encode it as true being 0, 0, 0, 0, 0, 0, 0, 1, and then false is 0, 0, 0, 0, 0, 0, 0, 0. Okay, how about analog to digital conversion? So the goal is to, let's say we are recording sound and we want to record a 10 millisecond sound wave, an analog sound wave in digital. And we are using a sampling precision of 8 different gradations and a sampling frequency of 1 kilohertz. Okay, so we have a sound byte. I shouldn't say byte. A sound thing of 10 milliseconds in length, and we are going to encode it with a sampling frequency of 1 kilohertz. So this is 1 sample per millisecond, and sampling precision of 8. So 8 gradations. That is possible values with which we can approximate each point in the sound curve, in the sound wave. It turns out that you would never sample anything with such poor precision, but I want to draw it on the board. When you download an MP3, it's usually sampled. You might know these numbers if you're used to working with this, but you're actually the sampling frequency is usually 44.1 kilohertz, and instead of 8 gradations, it's 65,536 gradations, which happens to be a 2 to the 32. But anyway, in our fantasy land, where we don't care how badly our music looks. So this will be the sampling precision. And this will be time. In milliseconds. And we're sampling a sound thing of 10 milliseconds, so we're going to go 0 to 10, and then say this is and we have 8 gradations, but starting with 0, so that means we're going to go 0 to 7, because 0 is a thing. 0 itself is a possible gradation. So 0, 1, 2, 3, 4, 5, 6, 7. And what we have is a sound wave that, let's say, looks kind of like that. So in order to sample this at the specified sampling frequency, we're going to do a really crappy job with this because there's a lot of detail in here that we're not going to be able to capture. But what you do is you go up to the you approximate sort of where this curve is on the x-axis, and you can't be between between spots on the y-axis, because that would be measuring as opposed to counting. We can only do this digitally. It has to be either 4 or 5. So at the second millisecond, it will be about here. Third, let's say it'll be about at the 5 again. Maybe at the 4th second, it will be about at the 6th. Be maybe at the 3 at the 5th. Probably 3 again at the 6th. 7 maybe at the 5. Kind of have to guess here. The 8th millisecond and the 9th millisecond are probably both of the same, and then 10, who the hell knows what's going on here? Let's say it's 4. This one is actually 2. Okay, so now we've done a really low resolution digital sampling of this signal, and we can encode it this digitally. So how many bits per sample do we need to encode this sample? how many bits per sample do we need for all 10? Well, if we have eight gradations, we can do that in 3 bits because we need 3 bits to 3 bits gets us 7, but 0 counts, so that gives us 8 possible gradations. We would never, in actual technology, encode anything in units of 3. We would probably encode this in 10 bytes of information, a byte being 8 bits. Okay, let's talk about the physical geometry of a digital recording medium that would actually be used to record this and bring it in this way to something that's nano-engineered. So an audio CD from 1982, and actually still today, if you go to the store, whatever stores still sell audio CDs, I buy them because I want the uncompressed sound. You get 783 times 10 to the 6 bytes. This is 783 megabytes, and these features are read with an IR laser. A DVD has a capacity of 5 gigabytes. This is read with a red laser. A Blu-ray disc has 50 gigabytes per data track, and it's read with a violet laser. So 50 gigabytes per data track, but there are usually 2 data tracks per side on a Blu-ray disc, and if you flip it over, I don't know if anyone's ever flipped over a Blu-ray disc, but if you had, you could get another 100 gigabytes on the other side between two data tracks. What does an optical storage disk look like if you chop it down the center? What you have is an injection molded polycarbonate piece. And just so I don't run out of time, I'm going to set my alarm. So you have an injection molded polycarbonate piece that you have fabricated by sort of a stamping lithographic method. So this is polycarbonate. And this is about 1 millimeter thick. This is a sputter deposited film of aluminum. And on top, you have an acrylic polymer. And up here, you have the label. Britney Spears' Greatest Hits, Volume 2. This distance here is about 100 nanometers. And the width of a bit, let me make sure I don't get this wrong. The width of a bit is going to be 600 nanometers for a CD, and about 100 nanometers for a Blu-ray disc. And here we have the information. And the information in the cross-section, this would be, say, this here is a pit. And this is a land. And we will say that the lands are 1 and the pits are 0. And we can have multiple pits and multiple lands in a row, and they're processed in units of 2 bytes at a time in a CD player or a Blu-ray disc player. And what happens is that there's a laser down here, and because this is aluminum, the laser is reflected, and you get you can, if the laser light strikes a detector, you know it's either a pit or a land, because it's going to be off by a few degrees if it's depending on whether it's a pit or a land. Interestingly, you can polish a CD. You buy like a polisher. This is I feel so old even saying this. You can polish a CD because the polycarbonate layer is so thick. It's like most of the thickness of the CD. And the data track, so this here is called the data track. The data track is very close to the label. So it's actually, if you scratch the label side with a knife and you gouge like 100 microns into it, you'll probably damage the data track. Whereas you can scratch a CD pretty deep and you can still polish it. A Blu-ray disc, the data track is actually closer to the surface because it's made of a harder plastic. But one time, so Netflix used to be in the business of sending you discs by mail. And in fact, if you want to get something that Netflix is not licensed to stream, you still have to get it that way, which is how I'm going through Game of Thrones right now, because HBO and Netflix don't have a deal, right? So I get the discs, but if you have a Blu-ray disc that has a problem, in the early days, you'd send it back and you'd check on the website that there was a problem with the disc, and they, not knowing that you can't polish a Blu-ray disc the same way that you polish a CD, would try to buff it out, and they'd destroy it in the process. Then they'd send it back to you, and it would be just full of scuff marks because they had tried to polish this side of a Blu-ray disc where the data track is right here. So they polish right into the data track and destroy it. CDs, Blu-ray discs, still relevant because actually magnetic storage media, which are also becoming irrelevant, but magnetic storage media work in the same sort of way, except it's not, you're not reading it optically, you're reading it magnetically, and you're reading it depending on whether or not the reversible magnetic domains are oriented north or south. Instead of a pit or a land, you have these orientations of the magnetic domains, which are similarly small in size, even smaller than in optical storage media. It's actually interesting to think about just how advanced optical storage media were. So the CD technology is actually 35 years old, but we're well within the nano regime, right? So if you have a CD from the top, and this is kind of the hole, and this is the transparent little plastic part. There's a data track that's like a spiral, just like an LP or a record, which I guess is actually becoming more popular, ironically. And what you have is a pitch in the data track. So this is a CD from the bottom view, the pitch of the data track is 1.6 microns. And if you take a little a zoomed in view of this piece of the data track, what you're going to find are the pits and the lands that look something like this. So you break the CD apart and you take it under a scanning electron microscope or an AFM. This is the kind of thing you'll see. You'll see that in cross section. You'll see this from the top. Unwound, this is it's 5 kilometers long. So take you 25 minutes or so to run the length of the data track if you were to unwind it. Pretty incredible for 1982. I'm pretty sure dinosaurs were alive then. So the total storage we said is 783 megabytes. The sampling rate is 44.1 kilohertz and 16 bits precision. And the number of gradations is 2 to the power of whatever the bit is. So that's 2 to the 16 is 65,536 gradations. So much better than we did here. But I wanted to be able to draw it in 2 minutes. And you need to multiply all this times 2 if you're talking about a stereo signal. This is all uncompressed audio. Nothing about MP3s or any of that stuff. So you need two signals, one for the left speaker and one for the right speaker, that are independently encoded in an uncompressed audio form. Now, how are binary signals processed? And they are processed by logic gates, which are composed of a system of transistors, which are semiconductor switches that you can turn on and off using a voltage. Sometimes the results of one computation will produce another computation, will produce the input for another computation, produce the input for another computation, and so on. But the basic units are the logic gates. And they come in a couple of forms. There's not, which is cool, not. Which says that if you have an input of 0, it's not 0, it's 1. If you have an input of 1, it's not 1, so it's 0. The symbol for the NOT gate is that. And is similarly intuitive. AB in the output is Q, 0, 0, 0, 1, 1, 0, 1, 1. And implies that A and B both have to be 1 in order for Q to be 1. So this is 0, 0, 0, 1. Or also means pretty much what you think it means. So their truth table 0, 0, 0, 1, 1, 0, 1, 1. If either A or B is 1, then Q is 1. So we have 0, 1, 1, 1. Symbol for the AND gate. 5 minutes left. Symbol for the AND gate is a double sticked popsicle. A input, B input, Q output. The OR gate best way to describe this is the Starfleet symbol. If we had to write an equivalent circuit for a NOT gate, or an AND gate or an OR gate, for the NOT gate we'd have like a voltage source hooked up to a light bulb, but then we have a switch here, which when closed, which would be the one, so this is a light bulb, and if we close the switch, so we make this from a 0 to a 1, then the light bulb goes off because this is higher resistance than this, we're assuming, and that would turn the light off. So this would be kind of how you would design a NOT gate in terms of switches. An AND gate would kind of be like where this switch would be like A, and the light bulb would be Q. The AND gate would be switches in series because both A and B have to be on in order for Q to light up. The OR gate could be similar to the AND gate, except that A and B are themselves in parallel, so that either A or B would have to be closed in order to give you the light at Q. Okay, so these ones are kind of the intuitive ones. Then you have NOR, which is not OR, which is like the NOT gate plus the OR gate. We have A, B, and Q, 0, 0, 0, 1, 1, 0, 1, 1, and our Q output is 1, 0, 0, 0, which should be the complete opposite of OR, which it is. And the OR gate is, or the NOR gate is the Starfleet symbol with the circle on it. And if we were to design the NOR gate with switches and lights and batteries and stuff, we'd have the switches in parallel, but in parallel with the light bulb. And convince yourself that this arrangement would give you this truth table. Then we have the NOT AND, or the NAND gate, which happens to be the most popular logic gate in an actual transistor in a computer, because from the NAND gate is the way to make all the other gates with the most efficient use of transistors possible. So NAND is very important. 0, 0, 0, 1, 1, 0, 1, 1. And our output is 1, 1, 1, 0. Our symbol for this is a popsicle with a little bit that's melting at the end. And if we had to design a circuit, it would look something like this, where we're cutting off the light bulb in parallel, but using switches that are arranged in series. So I'm going to draw two more, and I'll leave it to you to draw the equivalent circle or equivalent circuit model, and these are the exclusive OR and NOR. So this has to be, so this is called XOR. Zero 0 0 1 1 0 1 1, and it has to be exclusively OR. So if it's both, that doesn't count. So 0 1 1 0, and exclusively not OR is the opposite, and that is X NOR. We're really getting into sci-fi naming conventions here. X NOR. 0 0 0 1 1 0 1 1, and we know this has to be the opposite of XOR, so it's 1 0 0 1. And the symbols for this, the electrical engineers and philosophers got really creative here. So we have the Starfleet symbol plus some speed lines, or a spoiler. It's going real fast now. And then XNOR is the Starfleet symbol with the circle at the end and with the spoiler. So for fun, or perhaps for your homework tonight, you can figure out what the equivalent circuits are. On a microprocessor, they're not switches that you physically push with your hands, but they're actually transistors. And the transistors are controlled, open, and closed by a gate voltage that you apply. Next time on Friday, we'll talk about what a transistor is, how you make it using nanofabrication engineering. And on Monday next week, we'll do a PowerPoint lecture on how this is done industrially. Thanks.